Hello everyone, uh, welcome to another lecture as part of our ME 6151, the Computational Heat and Fluid Flow course. So in the past lecture, in yesterday's lecture, we looked at how to discretize the convection term, right? The rho u bar phi, the convection term that we have learned how to discretize it, and then we have also looked at one particular scheme of discretization that we named it as central difference scheme, that is CDS. Basically, where the phase value of the dependent variable phi e is expressed as a linear average or linear interpolation of the east and the primary phases, right? We wrote phi little e equals phi capital E plus phi p by 2, right? That's what we have done in order to come up with a value for the phi on the east phase, and that's what we call it as a central differencing scheme in the literature. Okay, now we also saw that this central difference scheme produces negative coefficients, and in order to avoid getting these negative coefficients, we have to choose our grid such that the cell Peclet number should be less than 2, less than or equal to 2, right? That's what we kind of discussed in the yesterday's lecture. Alright, so in today's lecture, we're going to look at an alternate scheme to the central difference scheme, that is known as an upwind difference scheme, which would not suffer from such a problem. Okay, and after looking at how to kind of work with the upwind difference scheme, we are going to look at the order of accuracy of the central difference and the upwind difference schemes. Okay, we look at what is the spatial order of accuracy, which we have done for the pure diffusion equation, right? We have established the order of accuracy to be second order accurate in space, but we will do it for now for the convection terms, that is basically with these particular two schemes, okay, with the CDS and the upwind difference schemes. Now finally, we will also look at an example problem of solving a pure convection problem using both these schemes, both the central differencing and the upwind difference schemes. Okay, so that is the agenda for today's lecture, and so let's move on with the upwind difference scheme. So if you look at the central difference scheme that we had worked on yesterday, we note that there are negative coefficients, and these were coming because of the arithmetic average, right? We wrote phi little e equals phi capital E plus phi p by 2, and only because of this we were getting negative coefficients, because the coefficient for here phi east would be fe by 2, and that would go in as to the a east as de minus fe by 2, right? So this is the reason we were getting the negative coefficients. If it was not a linear average, then we would not probably have got negative coefficients like this, and further those constraints on the Peclet number would not have been there. Okay, so in order to eliminate this kind of problem, people have proposed a different scheme, an alternate scheme, that is known as upwind difference scheme, and which primarily works on the direction of the mass flow rate. Okay, so that means let us consider this grid. So we have our P cell, east cell, and of course the west cell, and we have phi p stored here and phi capital E stored here. Okay, now in the upwind difference scheme, what we do is, depending on the direction of the mass flow rate, for example, let's say blue indicates arrow in the positive x direction where the mass flow rate is greater than or equal to 0. That means the flow is going this way. I mean, essentially, if you look at the definition of mass flow rate, it contains density, velocity, and the delta y. Delta y is positive, density is positive, so ue. So if the flow, if the ue is positive, that means fe would be positive, right? The flow is going this way. If ue is negative, fe would be negative, and it would be going in the negative x direction, here shown using a red color arrow. Right? Alright, so we have these two conditions. Now what upwind difference scheme proposes is that do not take the face value as the linear average as we have done here, rather take the face value as the corresponding cell value of the upstream direction. For example, if fe is greater than or equal to 0, that means then consider this phi east equal to phi capital P. Okay, this is the upwind direction. For example, as the flow is going this way, this would be the downwind direction, this would be the up of the wind, right? So essentially up of the flow. So that is the direction. So calculate, so assign phi little e equals phi p if fe is greater than or equal to 0. That is the first condition. If fe is less than 0, then take phi little e equals phi capital E. That means fe is in this way, then take the up direction. The up direction for this would be this one, right? Because this would be the downside, this would be the upside, right? From where the upstream, from where the flow is coming, right? So essentially this would be the upstream for a flow like this, and if the flow is going in the negative x direction, this would be the upside, right? So that means by definition the phase value is approximated using the cell-centroid value in the upstream direction, in the upwind direction. That means phi little e equals phi capital P if fe is greater than or equal to 0, otherwise it will be equal to phi capital E. Okay, so either phi capital P or phi capital E, purely determined by the flow direction or the upwind direction. Now you may have a question, okay, what about the diffusion, right? We might have had some diffusion by the time this phi might have reached this phi E. That is what we are actually neglecting here, right? If we are not considering the diffusion of the scalar within this half the grid cell size, okay, that is what is neglected in this particular scheme. Okay. Okay, now given that this definition, as we can see, we don't have, essentially there is no linear average, it's just equal to the upwind cell center value. Okay. Now, so as we can see, this is completely determined by the flow direction or the upwind direction, and the, let's say if we consider the east phase, we are only kind of focusing on the convection term, and you consider the east phase, the total convection term would come out to be f little e, phi little e, right? In the case of CDS, we wrote this as phi capital E plus phi p by 2, whereas now what we would do is, we would write depending on the condition. So we will have a conditional statement, that is, if fe is greater than or equal to 0, then f little e, phi little e would be equal to f little e, phi capital P. Otherwise, it will be f little e, phi capital E. Okay, so either this or this, depending on the direction of the mass flow rate or the direction of the velocity on the phase. Okay, that means we would need to write 4 such conditions for all the 4 phases, right? Depending on whether f east is positive or negative, you would get either of these coefficients. Similarly, depending on if f west is positive or negative, you would get 2 conditions, and depending on f north is positive or negative, you get 2 conditions, and so on, right? Okay, now a logical question would be, where will fe go? Where will fe go? Fe will go to either AE or AP, depending on the mass flow rate, right? Because if the mass flow rate is positive, then Fe would kind of go into AP, right? Because this is multiplying phi p, and if it otherwise, Fe would go into AE, right? Okay, we understand that. All right. Then let us move on in terms of how do we code this particular concept of upwind difference scheme when you want to solve a convection diffusion equation. Okay. So one thing would be to, first of all, discretize the equation as if there is no convection, right? First of all, let us look at the diffusion part of the equation. So if you were to write a final equation as AP phi p equals sigma NB phi NB plus B, then if the component coming from the diffusion is the same as what we have studied before, right? So that doesn't change. Only the convection part would have now conditional statements because of the mass flow rate coming into play. Okay, so what we can do is we can first assign these A and B's only with contributions from the diffusion. So A east would be essentially gamma E delta Y by del X E, right? That is nothing but your D east. Similarly, A W would be DW, that would be gamma W delta Y by del X W. Similarly, A north would be DN, which is given by gamma N delta X by delta YN. And A south would be D south, that is gamma south delta X by delta Y south. Okay, so far so good. These are only A considering the diffusion part, right? The contribution from convection needs to be still further added to A east, A west, A north, A south, which we have not done at the moment up till here. Okay. Now what would be AP? AP would be summation of all these neighbors, that would be sigma A and B, minus of course the contribution coming from the source terms, that is SP times delta Vp, as well as B would be equal to SC times delta Vp. Okay. So that's what we have. This is now let us look at the convection part. So the convection part, if Fe is positive, then what do we need to do? If Fe is positive, then you look at the original equation. You bring the convection term to the right hand side, right? We have gamma grad phi E dot AE minus rho u bar phi E dot AE. So essentially we are only considering the east phase. Then we have diffusion term, the convection term brought to the right hand side, plus we have the source term. Of course we have 4 such terms corresponding to the 3 other phases, west, north, south. Okay. Now what will happen if Fe is positive? If Fe is positive, then essentially if you look at here, this is your Fe, right? Rho ue delta y. Ae in this particular case is positive I times delta y. So this is this term can be written as minus rho ue delta y phi e. Essentially this will be minus Fe phi e, right? Where Fe would be equal to rho ue delta y. Alright, so that is your minus Fe phi e. Now if Fe is positive, then phi little e equals phi p, right? Then this will be minus Fe phi p. And if Fe is negative, if it is going in the negative x direction, then phi little e, the upwind direction, upwind value for phi east phase would be equal to phi capital E, phi cell centered value at the east cell. That will be minus Fe phi capital E, right? So this is essentially we are changing phi little e to either phi p or phi east. Okay. Now we have these two terms, minus Fe phi p or minus Fe phi east, depending on whether this is positive or negative. Okay. Now of course we know that if Fe is positive, this has to go to AP, and if it is negative, it has to go to A east, right? But then what will be the signs? That's where we are kind of explaining all these concepts here. So what will be the sign? So because this term is here, minus Fe phi p. Remember when we have written these equations, we have sent the phi p terms to the right hand side, right? We leave the source terms and the A neighbors on the left hand side. We send the p terms to the right hand side here, right? That means minus Fe phi p would be a contribution to AP with a positive sign. So that means if Fe is positive, AP would be equal to AP plus Fe. Okay. If Fe is negative, of course we know that this entire thing evaluates to minus Fe phi capital E, right? Because then we are replacing phi little e with phi capital E if Fe is negative. Fe itself is negative, but then you have minus Fe phi E. So what will be this contribution? This contribution of minus Fe would go into A east. Okay. So A east will be equal to A east minus Fe. Okay. Essentially this contribution, because it is getting retained on the left hand side here. Okay. Now one thing you notice here is because we have already populated the coefficients A neighbors and AP with some values of the diffusion terms, we are now adding to the existing value whatever is the extra contributions here, right? We are not writing AP equals Fe. That would be incorrect, because if you write AP equals Fe, then all your contribution of the diffusion is gone, right? We are essentially solving for pure convection problem. That is not correct. So AP needs to take care of the original AP where the contribution from the diffusion is already there, plus Fe, right, which is the convection part. Okay, so we need to write a conditional statement such that either AP or AE get modified because of the convection on the east phase, right? So we need to now write how many such conditions. So we need to write 4 such conditions, right, corresponding to each of the 4 phases, right? That is basically east, west, north, and south. Okay, so we need to write 4 such conditions. We will not write all the conditions here. Rather, I will look at the other phase, that is the west phase here, and I would leave the north and south for you to figure out. So if you look at the west phase here, so if we are on the west phase, that is W, then what do we have here? We have, if FW is positive, then AP is something I have written, else it will be blah blah blah, right? Either if FW is positive, contribution has to go to AP. If it is negative, contribution has to go to AW. Okay, we will look into that. So if you go back to the original equation, if I consider only the west phase terms, that means I have gamma grad phi w dot aw minus rho u bar phi w dot aw, right? So this is the diffusion term, this is the convection term, plus we have three other terms like this corresponding to three different phases, plus we have the source term, right? We have the source term plus equals 0, right? So essentially we brought the convection term to the right hand side to be on the same side as the diffusion term. Okay. Now what is AW here? AW is minus I times delta Y, right? That means what would happen to this entire term of convection? This would become a plus because AW is now minus. This will become a plus rho UW delta Y phi W, right? Phi on the west face. So what is rho UW delta Y? This is FW. So we can write this as plus FW phi W. Now if FW is positive, then what would be the upstream direction for FW? It would be, if FW is positive, the upstream direction would be FW phi W, right? This is the one because it has to be the right, I think it has to be FW phi W, isn't it? Because you have west P and east. If FW is positive, then it has to be FW phi W, and if FW is negative, then it has to be FW phi P, right? It has to be FW phi P if FW is negative. Is that correct? So that means what I'm saying here is that because if you see your mesh has W, and then you have a P cell, right? And then you have the east cell, right? So you have the W cell, the west cell. So if FW is positive, it is going this way, right? That means your phi W has to be phi little w has to be phi W, right? So this is when it is positive, and if FW is negative, it's going this way, then your phase value of little w has to be equal to phi P, right? That means what I have here, so this is when FW is greater than or equal to 0, and this is when FW is less than 0, right? If it is less than 0, phi west would be equal to phi P. Alright, but both contributions are now plus values. I think this has to be changed. This is not correct. So if FW is positive, right, then this is not correct. Essentially, this has to be, if FW is positive, then AW has to have AW plus FW, right? Because this contribution goes into AW with a positive sign, right? And if FW is negative, so this is not correct here. So you need to modify this. This is not correct. This is when FW is this is when FW is less than 0. Then the condition is that if it is less than 0, then the contribution has to go to FW. This, because it's multiplying phi P, it has to go to the right hand side. Okay, so it has to go to the right hand side. That's why there is a minus. So AP would be equal to AP minus FW, and otherwise if FW is greater than or equal to 0, then your FW phi W would be equal to FW phi W for the west. That means the contribution is going to AW. Okay, so you need to fix this one, but otherwise this is fine. Okay. Okay, I hope you understand this part here. All right. So now you need to, of course, write two more such expressions, one for the north face and one for the south face, which I'm not going into it right now as such, but you can reduce it and write it the same way. All right. Okay. Now, all right. So this is one way to implement the convection diffusion equation. The other way to implement is basically to get rid of all these if-else statements. You can write one particular general algorithm for the Upwind difference equation by defining a max function. What is a max function? Max function is something that finds a maximum of two variables. This is very much available in either C or in Fortran. So this is or in C++. So max of A, B, if where A and B are two real numbers, then it would give you A if A is greater than B, okay, or it will give you B if not, okay. So essentially whichever is the maximum will be returned by the max function. Now this can be a very good tool to compactly write the Upwind difference scheme rather than writing so many if-else statements, okay. So instead of writing so many if-else statements, we can just write a very compact method for the Upwind difference scheme using this max function. Alright, so I'm going to kind of tell you what it is, and then you have to double check, you have to verify whether it is correct or not, okay. So essentially we seek to write AP phi p equals sigma NB phi NB plus B, okay, and our A neighbors, A capital E, is now D east, right? This is basically what is D east? This is coming from your diffusion, right? These components are coming from your diffusion, right? These are all coming from your diffusion, and then this is the convection part, right? So we would not worry about these things, which is basically same as before. Now in the convection part, what we say here is that in the convection part, we know that depending on the direction of FE, the contribution will either go to A east or it will go to AP, okay. So what we do is, let's say if our FE is positive. If FE is positive, that means it's in the positive X direction, then the contribution has to go to AP, right? That means if FE is positive, max of minus FE comma 0 would return what? This would return how much? This would return a 0, right? Because FE is positive, minus of positive and 0, maximum is 0. So 0, that means AE will have no contribution, because the contribution of positive FE has to go to what? FE times phi P, right? Because phi little e is now phi P, because FE is positive. That means FE has to go into the contribution for AP, right? It has to go into contribution for AP. So as a result, we add FE here in the AP equation, okay. So basically this is bringing in only DE, so the DE goes in here, minus SP delta VP plus FE, okay. I'm only focusing on right now on the east face, so I'm only looking at A east, this guy, and the AP. Alright, now that is fine if your FE is positive. What if FE is negative? Then the contribution has to be added to A east, and there should be no contribution to AP. But because we have written it here, this may not be correct. So let us check that. So if FE is negative, what will be returned with the maximum of minus FE comma 0? What will this function return if FE is negative? FE is negative, this function will return minus F east, right? Because FE is negative, this will return minus F east, isn't it? Because minus FE would be bigger than 0. Okay, so if minus FE comes into play, your A east equals DE minus FE. Would that be the same as what we had before? Right, so if FE is negative, A east equals AE minus FE. That is correct, okay. That means this is fine. But what is the contribution for AP? AP has to be 0. So this brings in A east, brings in DE minus FE. So we have DE minus FE here, plus we have this FE. So FE gets cancelled with this extra FE minus FE coming, and then we essentially have DE. That means there is no contribution of FE going into AP. Okay, do you see how it is working? Yes. Alright, the same is the case for F west. Let's say if F west is positive, F west is positive, that means what will this be? This will be F west is positive, so this would what will be returned would be FW, and this term would evaluate to FW. Because it is positive, the upwind direction would be phi W, right? So essentially the contribution has to go into AW, right? Contribution has to go to AW. That means FW is positive, max of this would be FW, and it would read FW phi W. So essentially AW will have a contribution. So, but when that AW gets added here, this will be DW plus FW, but there is a minus FW. So as a result, there is no contribution to AP. Okay. Now what about if you have Fw is negative? This is, let's say, minus Fw is negative, then what will be returned by this max of Fw comma 0? 0, right? Fw is negative, so max of Fw comma 0 will return 0, right? That means there is no contribution to Aw, because if Fw is negative, then what will be the total value? Fw Vp, right? That means there is a contribution going to AP, isn't it? Okay, so that means A west will have no contribution, but when you come here, there is a contribution of, there is nothing that is coming into sigma and B through these guys, but there is minus Fw. Minus Fw because it will be gone to the other right hand side. Okay, so that means minus Fw Vp and then Fw Vw. Is that correct of what we had? If Fw is positive, then the contribution has to go to Aw, which is Aw plus Vw, and if it is negative, it has to go to minus Fw. So this is correct. Okay, fine. So what we discussed is corroborates with this function. Now I am not doing it for these two quantities here, so you have to do it yourself for the north face and for the south faces. Okay, so for the north face and for the south face, you have to do it yourself, verify whether this is working or not. Okay, as a result, what we have is we have a nice compact algorithm without having all these if else statements. We just have a max function, we code it up, and then both the diffusion and convection parts come into play here. Okay, so we have A east, A west, A north, A south, and AP would be equal to sigma NB minus SP delta VP plus F east minus FW plus F north minus F south. Okay, this is required, and B equals SC times delta VP. All right. Okay, that is kind of very compact thing than the if else statements. What about the coefficients now? Okay, so if you look at the coefficients, what is the property you have? All the coefficients are now positive, isn't it? If F is like the diffusion coefficients are always positive, these are always positive. What about the convection parts coming into play? If this is negative, this will become positive, it will be returned. If this is positive, this will be 0, right? Either this is always positive or 0. That's what is happening. That means all A east, A west, A north, A south would always be either 0 or positive, right? That means we'll have 0 or positive contribution coming from the convection terms. That means A and B are all positive. Now what repercussions does it have on the Scarborough criteria and on the boundedness if they are all positive? We are happy because if they are all positive, we can satisfy some of these properties. Let us say if there is no source, S equals 0, and for the incompressible flow, it satisfies continuity equation. So if the underlying flow field that is given to us, let's say, satisfies the continuity equation, right? It satisfies the mass conservation. Okay, that means if it satisfies mass conservation, what will happen to this term here that we have? The Fe minus this entire term would be what? Would be equal to 0 because it satisfies mass continuity, and the source term is also 0, so this term is also not there, right? In that context, what would be your AP? AP equals sigma NB, right? If there is no source term and the given flow field satisfies continuity equation, then AP equals sigma NB. We also note that all the NBs are positive. Okay, all the NBs are positive. That means AP equals sigma NB, and also we have AP Vp equals sigma NB Phi NB. So essentially it satisfies Scarborough criteria. So Scarborough criteria is satisfied, right? In equality. Okay, satisfied in equality. What about boundedness? Of course, it is also boundedness is guaranteed, right? Because AP Vp equals sigma NB Phi NB. So boundedness is also guaranteed. All right. So what we see is that we have now developed a new scheme which satisfies the Scarborough criteria as well as boundedness, which is much better than what we had before, and there seems to be, there is no condition on the coefficients, right? and mesh can be taken to be anything, right? Unlike central difference scheme where the mesh size is kind of restricted by the cell Peclet number that we have. Okay, so far so good, but it turns out that the upwind difference scheme is quite diffusive. Okay, it's very diffusive, and even with by taking say finer grids, this can actually smear out the discontinuity. So if there is a discontinuity in the problem and there is no diffusion given, let's say gamma equal to 0, and there is a discontinuity in the solution of phi, then it can actually smear the discontinuities. Okay, so it turns out to be very diffusive. This we will explore this behavior with an example problem little later. So that because of this, UDS can be used as an initial solution, but it is quite diffusive. As a result, we will look for some of the high order upwind difference schemes which are better in terms of not having such high diffusion such as the UDS. Okay, so we'll look for some higher order schemes as well little later in the course. Okay, as of now we have learned these two schemes. One is the central difference scheme, the other is the upwind difference scheme. Okay, so both of them we have looked at in terms of their properties and how to implement them in a particular code. Okay, let us move on to the next concept, that is basically we have not actually looked at what will be the order of accuracy of these central difference scheme and the upwind difference scheme. Okay, so the order of accuracy, again for this I would resort to a basically a uniform mesh, and I would also look at a one-dimensional problem with let's say uniform properties in order to look at the order of accuracy. So we have a 1D problem with uniform mesh, that is delta x is the same for all the cells, and then we have the P cell, east cell, W cell, and the east and west faces here. Now as usual I would use the Taylor series expansion here. Okay, so use Taylor series expansion, and then using this expand phi p about phi little e. Okay, that means phi p is phi little e and the distance is minus delta x by 2. So this will be minus delta x by 2 d phi dx at the east face plus delta x by 2 whole square by 2 factorial d square phi by dx square on the east face plus order delta x cube and so on. Okay, similarly let me expand phi capital E about phi little e. Okay, so this would be at a distance of plus delta x by 2. So phi capital E would be phi little e plus delta x by 2 d phi dx on the east face plus half delta x square by 4 d square phi by dx square and so on. You get all positive coefficients here, you get a negative here, and this also has to be a negative. Okay, fine. Now from one of these equations we can write let's say phi east equal to phi p plus some order delta x, right? If you send these guys to the left hand side, then phi east equals phi p. Now what are we doing? We are saying in the upwind difference scheme, let's say if your Fe is positive, we are saying take phi e equal to phi capital P. So what does that mean? That means by this approximation, what is the order of accuracy of the scheme? Order of accuracy is only order delta x, right? It's only order delta x. So that means the upwind difference scheme is only first order accurate. Similarly, if Fe is less than 0, we say that phi little e equals phi capital E. That also gives you an order delta x for the downwind, for the upwind direction, right? If the mass flow rate changes. So upwind difference scheme is only first order accurate in space. Okay, that needs to be kind of understood. Then what about the central difference scheme? Central difference scheme, what we're doing is that we are saying phi little e equals phi p plus phi e by 2. Okay, then let us add these two equations and divide by 2. That means add equation 1 and equation 2 divided by 2. Then we can write what is phi east equals phi east plus phi p by 2, and there is a 2 times phi e by 2, so this will be phi little e. This term gets cancelled because we are adding, and this term becomes delta x square by 8 here and 8 here, so this will be delta x square by 4, but then we are dividing by 2, so this will be delta x square by 8. And when we send to the right hand side, what we get is a minus delta x square by 8 d square phi by dx square, and the next term here would be order delta x to the power 4. Okay, that means in a central difference approximation, when we say phi little e equals phi east plus phi p by 2, the truncation error we are making is basically order delta x square, right? So this is the truncation error we are making. This is about second order accurate. Okay. So what we see is that although CDS is second order accurate, it comes with a condition on the simulation on the mesh refinement, whereas upwind difference scheme is only first order accurate, but it has no condition. However, upwind difference schemes are very diffusive. Okay. We will also see that the central difference schemes kind of are kind of dispersive, or basically they produce oscillations if you don't meet the Peclet number criteria. Okay, so essentially the question remains is, then how do I solve for convection? What we are saying is that if you use CDS, there is too much restriction, and if you use upwind difference scheme, then there is too much diffusion. What do I do? Then the answer is you go for a higher order scheme that is constructed based on the upwind difference schemes. Okay, that is the kind of answer. So look for higher order schemes, which we will learn in little while into the course. Okay, into a few more lectures in the course. All right, let us look at this then the final part of today's lecture, that is basically an example problem. So what we want to discuss is, let us look at pure convection. Okay, that means we are setting gamma equal to 0. There is no diffusion, there is no source term. Okay, so basically no source and no diffusion. Okay, so it's only pure convection. That means the equation, and it's also steady. So what we are solving for is basically del dot rho u phi bar equals 0. Okay, just convection, and the given velocity field is basically is something that is flowing at 45 degrees, right? We have one I cap plus one j cap, so it's flowing at theta equal to 45 degrees from the x-axis. So this is the flow field. It kind of goes this way and leaves the domain. Okay, we are also considering a square domain with dimensions L by L. That's what we are considering, and there is no diffusion, but we are interested in how does the scalar get transported. So we have the scalar given a value of phi equals 0 on this vertical boundary. Okay, so it is basically given a value of phi equals 0 if I were to draw it with the blue. So the value of phi on this vertical boundary is 0, and the value of phi on the horizontal boundary is given as 1. So we are interested in if there is no diffusion, how does this 1 value and this 0 value get convected into the domain because of this flow field? Well, it is very simple. If you essentially release some dye here, this dye is going to convect and it is not going to diffuse because there is no diffusion. So that means everything, and because the flow is angled at 45 degrees, everything that originates from here would go, and this entire thing would get filled up with phi equals 1. So this entire thing would be phi equals 1, and whatever is on the top would be phi equals 0, right? So essentially this entire thing would be filled with phi equals 0, and right, this entire thing would be filled with phi equals 0, but then there is no diffusion. That's why you will see an abrupt jump in the along the diagonal. You would see an abrupt jump between phi equals 1 and phi equals 0, right? There is an abrupt jump. However, if there was some diffusion, then there will be a kind of a layer that gets formed between these two, right? In which the value of phi would change from 1 to 0 through some diffuse layer. Now the thickness of this layer would depend on the amount of diffusion you have. If you have larger diffusion, this layer would be thicker and thicker, or in limit of gamma equal to 0, this will also be 0, right? So this layer kind of thing would exist in which the phi value will change from 1 to 0 in this particular along the diagonal. Okay, but for the present problem we don't have this gamma, so as a result there is no such layer. Okay, so this is the exact solution. Now if you were to calculate the cell Peclet number, which is given by rho mod u bar delta x by gamma, what would this value be? This will be infinite. Okay, or if I write a Peclet number for the entire domain, instead of calculating the length scale as delta x, if I take the length scale as capital L, this entire thing would come out to be also infinite. So the Peclet number is infinite. Then what does that mean? Peclet number is infinite. Then what would be the what should be delta x, right? What delta x should I take if I am using central difference scheme? What delta x should I take? There is no delta x I can take, because which satisfies this problem, because Peclet number is infinite. That means delta x has to be 0. So even if I take smaller and smaller mesh, it will never satisfy this condition of Peclet number less than 2, right? Because gamma itself is 0. As a result, delta x has to be also 0. But then that is impossible. That means for any delta x that we take, we are going to see some kind of oscillations if you solve this problem using a central difference scheme. Okay, and we will see that if you solve this problem using an Upwind difference scheme, then what you see is that you see some kind of an artificial diffusion which is not there in the original problem specification, right? Okay, so let's say if I were to travel along this vertical line, okay, I go from y equals 0 to y equal to L, what will be the solution phi change look like? So phi would be equal to 1 all the way to y by 2, and it will be equal to 0 from y by 2 to y, L, isn't it? So this will be 0 to L by 2, phi would be equal to 1, and L by 2 to L, phi would be equal to 0. So essentially we see a step function with 1 here and 0 here. That would be the exact solution that is expected from this problem. Okay, we would kind of draw that. So the exact solution is given by, as we go along the y-axis, if I plot the phi, then the exact solution is phi equals 1 until I reach L by 2, and then it will suddenly drop to 0 and it will come to some value here. Now if you solve this problem using, let's say, 15 by 15 cells, using both the central difference scheme and the Upwind difference scheme, what you notice is that with the central difference scheme, the results are shown in red here. What you get is you get some kind of an oscillations. Okay, so you see these artificial oscillations or false dispersion. Okay, this is what we call it as, this behavior of oscillation we call it as dispersion. And if you had solved this using Upwind difference scheme, what you see is that you essentially get a smooth curve, right, that kind of goes like this, which shows there is some diffusion in the problem, right? But however, there is no diffusion, right? But we know that the gamma is equal to 0, right? So what we see here is basically some kind of a numerical diffusion that is basically an artifact of the Upwind difference scheme. Okay, so that's what we see here. So as a result, this is not none of these things kind of give an exact solution. Okay, so that is the behavior. Now these two behaviors are known as either artificial, numerical, or false dispersion, which is this one, the oscillations, the Gibbs phenomena we see here, and then the artificial or numerical dissipation, which is given by the Upwind difference scheme. Okay, now these two is what we will elaborate in the next lecture, but it is good to know that this kind of behavior exists when you try to solve a pure convection problem with any of these schemes. Okay, now one question you may have is what if there is some diffusion that is given in the problem statement instead of taking gamma equal to 0. Now depending on the value of gamma you have, the Upwind difference scheme will still produce some more diffusion. Okay, now depending on the value of gamma you have and depending on the delta x that you take to particularly satisfy Peclet number less than 2, you may or may not see these oscillations coming because of the central difference scheme. Okay, so that is the answer. We will see, depending on how it goes, we probably will solve one assignment problem on this convection diffusion problem or so. Okay, okay, then I'm going to stop here because that's kind of the end of whatever we want to discuss for today. Then I will talk to you in the next lecture. Okay, all right, thank you.